All right. Well, the William W. Hay Railroad Seminar Series is sponsored here at the University of Illinois at Urbana-Champaign by the National University Rail Center. This is a U.S. Department of Transportation University Transportation Center, and we thank the U.S. DOT for their ongoing support both of this seminar series and everything else that we're doing in the context of the new Rail Center. So let me take a few moments to introduce our speaker and his topic. And the continued increase in both total tonnage and axle loads on mainline freight lines, as well as the increasing performance needed by higher speed trains from the track system, is placing ever greater demand on the infrastructure and its components. One of the most critical areas of infrastructure in need of research are concrete crossties and the elastic fastening system, which is widely used to secure the rail to the tie in these most demanding heavy axle load and high-speed rail conditions. Thanks to support from a number of private and public sector organizations and the excellent leadership of our speaker today, the University of Illinois has developed a major research program in this area that's addressing a number of important questions and attracting widespread interest and attention in the domestic and international rail engineering community. The ultimate goal of this research are data, experimental results, and sophisticated new models that will provide a thorough basis for a mechanistic design process for the concrete tie and fastening system. Our speaker today is my friend and colleague, Riley Edwards. He's a senior lecturer in the Rail Transportation and Engineering Center here at the University of Illinois. He completed his bachelor's degree in civil engineering from Vanderbilt University in 2004, after which he was employed by the CN as a construction inspector on their Intermodal Gateway Memphis project. Then, after working at CN, Riley began his graduate studies here, where he completed his MS in 2006. And while he was a student here, he was awarded I was actually one of the very first recipients of the CN Research Fellowship in Railroad Engineering here. And this has been a major basis for one of the major bases for the expansion of our rail program in the last decade. Following graduation, he was drawn back to Memphis, but he switched railroads, actually switched companies. He went to work for Hanson Professional Service as a construction engineer, working on the BNSF Railway's Memphis Intermodal Expansion Project. In October 2007, however, Riley decided his true heart lay with academia, and he accepted a position here as a lecturer. His research interests are concrete railway crosstie and fastener design and performance and automated inspection of railway infrastructure. The research we'll be discussing today is sponsored by AAR, Amstead Rail, Amstead RPS, Federal Railroad Administration, Kansas City Southern, NextTrans, and the New Rail Center, and is being conducted in collaboration with a number of railroads, engineering, and railway supply firms. Please join me in welcoming our speaker today, Mr. Riley Edwards, who's going to be talking about this concrete tie.
All right, thank you, Professor Barkin, for the introduction and the opportunity to speak at what I guess is my second Hay seminar. While I was with Hanson Professional Services, I was fortunate to give a Hay seminar on some of the work that we were doing in Memphis, but this is quite different work and really represents, as the title slide shows here, the summation of work that's been completed by a rather large team. So first of all, in addition to myself, who in this room has been involved in just raise your hand, it's kind of hard to stand up, who's been involved in the concrete cross tie and fastening system work? So you get a feel. So these are these people, they may be CPR certified to save your life, but they also are going to help you learn about concrete cross ties. Usually at the beginning of these meetings, we raise our hand on a safety briefing to figure out who's CPR certified. So there's about half the people in the room here, for those of you online, that have been involved in concrete cross tie and fastening system research. So we've got an amazing team, and I'm very grateful to all these folks for their involvement. I want to bring up three things before I start into the technical content. These are the three most important moments in research funding history for this particular work you're going to see today. The first is the promise of funds from the AAR's Technology Scanning Committee, led by Dave Davis and others around the industry. They funded some feeder projects that allowed us to meet some key people in the industry and get started. Second is the funding that came from Amstead Rail and Amstead RPS. This was work that has been conducted through Jose Mediavilla and Brent Wilson, and was absolutely critical in taking us to a point where the third major event happened, which was the award of a very large FRA-funded broad agency announcement research project. We're going to talk a lot about it today, but Cam Stewart's oversight and Hugh Thompson from the FRA, it's very much appreciated your funding and what you've done to bring this team together. So here we go. I don't want to tell you how many slides I've got, but I'm going to go really fast. So I know people in here might be thinking about unofficial or other things that are going on today, so you're not going to be thinking about that the next hour, because there are going to be too many slides flashing up here. So what I want to start with is some background and research justification on this topic of concrete crossties. So where are they used? And this is referring to North America. So they're used in freight, passenger, and transit applications. On the freight side, they're typically used where we have heavy tonnage, steep grades, and high degrees of curvature. Each railroad kind of has their own philosophies as to where to install these concrete crossties and fastening systems. On the passenger side, it's typically high-density corridors such as Amtrak's Northeast Corridor, and in transit applications, typically transit agencies don't like to be out doing a lot of maintenance, so they can justify at times the higher cost associated with concrete crossties. So many of our transit agencies are installing concrete crossties. So how many of these do we have in the U.S.? This is our team's estimate that we have about 25 million concrete crossties in the U.S. on freight railroads, about 2 million on passenger, most of which are on Amtrak, and significant quantities that we can't exactly wrap our mind around on the transit properties. So this gives you a feel, especially when you think about some of these components, that there are actually 4 components per crosstie that I'm going to talk about in a minute that are up here on the front table. It's a significant number of infrastructure components. Yet concrete crossties still only make up about 7 to 10% of the North American infrastructure, but these are these very demanding locations as are described on the left. So what are these concrete crossties and fastening systems? Some people in the room may not be familiar with them. So it's a system made up of a group of components. First of all, we have the concrete crossties themselves. This is a picture of some that were being experimented on up at our H-Rail facility. We also have rail pads, and there's a bunch of examples of rail pads up here on the front table. I'm realizing it's going to be too far to go over there, so can I request a Vanna White type that will help pass some of these things around for me? It needs to be somebody on our team. Chris, Thiago, somebody there. So maybe send a couple of these pads around so you can see what these pads look like. There's all different varieties of pads, and we have many varieties of clips. So just pick a couple of pads and a couple of clips to send around the room. These are 4 major types of clips that are used throughout the North America and throughout the international community for that matter. We have insulators, many different types of insulators, and finally we have these shoulders. And as I'll show in a second, the shoulder, what it actually does is allow you to embed the fastening system into the tie. And each of these components has to work together as a complete system, and you effectively pick one from each of these categories to come up with your system, and hopefully they work well together. Sometimes they don't, and that's part of what we're going to talk about in the presentation today. Here's what the whole system looks like. Each one of these components that are being passed around, whether it be the rail pad, the clip, the insulator, or the shoulder. Once you put them together, you have a nice looking system like this. This drawing is courtesy of Mr. Williams on our team. So the system, the key component really is still the concrete crosstie, and that's what most people talk about. Our team likes to focus just as much on the fastening system, but a couple of words on the concrete crosstie really quickly. In North America, they're predominantly pre-stressed, precast products. There are a couple of instances in Mexico especially where we use post-tension ties, and you can actually see a couple of these ties in and around Newmark Lab. Ryan Kearns, one of the research engineers that I'm ably assisted by, can show you some of those if you'd like to see a post-tension one. So there's all different permutations of the system, and when you put them together and you go out in the field, you have a system that's hopefully operating well holistically. So one of the things that we've heard and what led to this research is it was our understanding that there's significant performance challenges with some of these components. So what this did was led us to conduct 2 different studies, the second of which was conducted in 2012 by graduate student Brandon Van Dyke, and it allowed us to survey the international research community to ask, what are the most critical problems that you have on your concrete crossties and fastening systems? So what we found out in North America, which is where our research sponsorship is coming from, is that the deterioration of the concrete material beneath the rail, which is sometimes called rail seat deterioration, and fastening system wear or fatigue. These are some of the the most critical problems. And the areas down here at the bottom that are highlighted in orange are areas that we're addressing with our current research program. So we're excited to be addressing a lot of problems that the railway industry deems critical. In addition to just these critical problems, we wanted to survey the international community and find out what are the research needs out there. Where would you see our team being able to make the greatest impact in this particular realm? And what we found out is that between the international community and the domestic community here in North America, we see almost a complete flip in terms of the priorities for research needs. And I'm There are a lot of reasons for this. They go well beyond the scope of this presentation. Any of the graduate students, anybody that raised their hand a couple of minutes ago can explain this in greater depth. But the cool thing is that at the bottom down here, you can see all of the North American research needs we're addressing through our program. And I'm going to describe in just a minute how our holistic program addresses them. So here we are with RailTEC's Concrete Tie and Fastening System Research Program. The way I like to look at it is we have three key categories or research levels. We have materials level research that's being conducted, component level research, and system level research. And within those blue blobs there on the screen, you can see some of the different projects within each one of those areas. But on the materials side, I'm ably assisted, and many of the projects are being led by Professor David Lang. We also have component level projects that allow us to investigate stresses and strains within individual components, and then there's some amazing system level work that we're doing that is kind of all centered around the development of a finite element model. Here's our current research sponsors. As Professor Barkin read some of these earlier, and I'm very grateful. Each one of these sponsors fits into their own special niche within the previous slide, and it's amazing to have partnership with these organizations, friendship with the individuals that make up these organizations, and it's great not just for the faculty but also for the graduate students, and we're very grateful to these groups. So here's who we're working with right now. And what I want to do next is go through three slides that mainly show you, I've already talked about our human resources. You've seen the hands go up of the people that are actually conducting the work. What I want to show you over the course of the next couple of slides are the tools that we use, which are only as good as the plan that you develop to actually use the tools. But you're going to see some of the tools here that we've used to conduct some of the research that's going to be presented on later in this presentation. I'm just going to cover these at a high level. You can ask any of the students that were involved in this work for further information. But on the left here, we have a large-scale abrasion test that was managed by Ryan Kearns while he was getting his master's degree here that allows us to replicate actual field loading conditions and generate abrasion on mock concrete rail seats. On the right-hand side of this slide, you can see work that was initially started by graduate student Amogshir Pali and is being continued by Emily Van Dam that allows us to test the abrasion resistance of different concrete mix designs. At the component level, by the way, this was at the materials level, what I just covered. At the component level, we have a static tie tester that you can see down in the Newmark crane bay right now. There's some work going on by Ryan Kearns using that machine right now if you want to go down and see how it operates. And also we use some of the other equipment that's in and around Newmark, like uniaxial testing machines, to conduct tests on rail to understand how stresses are moving throughout the rail as they're entering our fastening system. At the system level, here's a couple of our frames that we have at present. One of them is the pulsating load testing machine, which is owned by Amstead RPS. This is housed up at the Advanced Transportation Research and Engineering Laboratory, known as ATREL, in Rantoul. And we also, at ATREL, have a static tie or a static load testing machine that we use for some experimentation. So those are our laboratory system devices. Now we have what we have in the field is a stretch of concrete ties at the Monticello Railway Museum in Monticello, Illinois, which is, to our knowledge, I've said in previous presentations, the only stretch of Class 6 or Class 7 track on a museum railroad in North America. So we're pretty pleased with that 15-tie stretch. We also have two installations at the Transportation Technology Center in Pueblo, Colorado, and we'll be talking about these later on in the presentation. So those are the tools that we have to conduct the research. As I talk about some of the results here later on, you can think back to those specific tools that were used to generate the results. I can't go into significant detail on each one of those tools, but we got the brain power in this room to answer any questions you may have about those tools. So what really ties our whole program together is the vision for mechanistic design. As Professor Barkin mentioned in the introduction to this particular presentation today, we really want to come through very clearly to our sponsors and to the industry as a whole, showing this theme of mechanistic design. And what I'm going to do is I'm going to walk through a couple of slides that explain it. First of all, you should understand the current design process for these concrete cross ties and fastening systems. The current design practices are found within the ARIMA manual, and they're recommended practices. They are developed based largely on practical experience through a iterative design process, and they don't necessarily consider failure mechanisms and the causes. So there's other elements that are challenging. This is understood by the ARIMA community that has developed these recommended practices, and we're doing things here at the University of Illinois to aid ARIMA, or more specifically ARIMA Committee 30, in revising these. The principles of mechanistic design are as follows, and I'm not going to read through all of these. What I want to do is give you a high-level overview of what we're trying to do with mechanistic design. This has been employed in other industries and applications, and what we're effectively trying to do is capture the loading conditions at each interface and at each component within the system, and based on those actual loading conditions, design components that meet those requirements, and effectively, in the end, design a system that has at the component level all of the mechanistic design practices met. So you can read through these on your own. This presentation is going to be posted on the web after we're finished, or it may already be on the web now. I'm going to talk about a few of these today, especially how we actually quantify the loading condition at each interface. That's a major thrust of this research effort. So now I'm on slide 22, which is determining system input load. So step one, if we went through those other slides in great detail, we'd realize that step one is somehow establishing or quantifying our loading environment in terms of collecting data and actually analyzing that data. So there's a lot of different methods that we could use to actually figure out what loads are entering the track structure through the wheel rail interface. So here's some of the different methodologies: wheel impact load detectors, instrumented wheel sets, truck performance detectors, and then our very own homegrown UI/UC instrumentation plan, which, if I fail to mention this later, was developed in conjunction with some key people in the industry, not the least of which is Harold Harrison and Mike Thomas, who many of you all online probably are very familiar with. So these systems that we're using and the data collection methodologies that are out there right now are largely developed around the need to collect data for the mechanical side of railway engineering, for the health of the rolling stock. But we're going to try to take that information and glean we're going to try to take that data, glean useful information out of it that we can apply to the design of infrastructure. There are limitations to each one of these types of data that we could talk about in great depth, but for right now what I want to do is talk about wild data. You can see some of the limitations at the bottom, but for right now we have effectively nothing to go off of, so we're trying to start with wild data, which is a well-established system of understanding the impact loads and the actual loading environment. The next few slides that I go through, this is work that's been managed by Brandon Van Dyke. He's done an amazing job, and what you can see here is that the key takeaway from this slide is that when we have shared infrastructure, we have all types of divergent engineering requirements in terms of the actual loads that are applied to the infrastructure. So you can see the peak vertical load is along the x-axis, and the percent of impacts, or the percent of loads that are exceeding these various thresholds, is on the y-axis. So for example, at this range of about 27 kips, or about 125 kilonewtons, you can see that there's a significant disparity between the locomotives and the passenger coaches. There's about a 90% difference in terms of the percent of wheels that are exceeding that limit. So we're trying to design these shared corridors, shared infrastructure around challenging requirements like this. Another way to look at it would be on a chart like this that shows our nominal load and kips on the x-axis and our peak load on the y-axis. So this gives us some vision for what the impact factor is. We apply a nominal load and then we get a peak actual load out of it. So what is the magnification factor? And you can see that on this particular corridor we have coal traffic, which consists of empty coal trains and loaded coal trains that make up the two red blobs on the screen here. And we also have passenger coaches. And the spread of these data points upward, is my mouse show? Oh, great. The spread upward here tells you something about the distribution of the impact loads of these different types of freight cars. So what I want to show you next is, I mentioned the term impact factor and impact loading. Well, it's a major parameter for the design of these concrete cross ties and fastening systems. So at present, if you flip through the ARIMA manual on recommended practices, you would realize that there's an impact factor of 3 that's required at present. And you can see that based on this data that was collected on Amtrak, and we appreciate both Amtrak and Union Pacific for providing a lot of wild data for us, you can see that we have about 2% of loads that are exceeding that currently used predictor for impact factor. And impact factor, I'm sorry if I didn't say this earlier, it's just the peak load divided by the static load. And at this point, we also have included the locomotives in this diagram. So this just gives you a feel for how complicated shared infrastructure is in terms of design. And it leaves us with very important questions. By the way, this work within a couple of months is going to be complete. Brandon's churning through data right now. We're really excited about what we're going to show with respect to what's actually needed in terms of impact factors that represent the loading conditions that are actually seen out there right now. So this leaves us, this spread of data leaves us with the question of what should our design threshold be? So down there on the x-axis, you could think of any load. It could be the load, the rail seat load as is shown down there, or maybe those of you all that have the insulators, the little plastic insulators in your hand, it could be the load that's being transferred through that insulator. So whatever you want that x-axis to be, we need to look at what the frequency of loads are that actually are being input into that parameter, and then determine, based on our knowledge of how these materials fail and how they're actually designed, what is the design threshold. And this needs to be repeated for each component, interface, and failure mode. So where is this going to take us? Well, this particular conversation here is a point of reference. This is a conversation that we're going to continue with with BASF Corporation, one of the suppliers of the plastics that actually are injection molded to make these pads and insulators. So we're trying to figure out where are the design thresholds once we have the data, and where are we actually headed in the long run? Well, we want to develop this quantitative loading model based on all the wild data and some of those other types of data that we're also obtaining. So as a function of speed, for instance, what is the peak vertical load for different car types, and what is the confidence interval around it? You can imagine this is very noisy data, so there are a lot of variables associated with the health of the rail car and the wheels specifically. So this is where we're heading, and thus far what our data shows is that speed is not a critically important input into this determination of peak vertical wheel load, and we have reasons to believe that. We have reasons that we've documented to understand why that is the case. Ultimately, this is what we're going to deliver as our output to the industry in terms of being able to understand what loads are actually imparted on the track structure. So we have on the x-axis down there our nominal wheel load, and on the y-axis we have peak vertical wheel load. So you enter this graph, you know your nominal wheel load and roughly the type of rail car that you're going to use. It's important to know the type of rail car because the suspension system has a major role in actually how the loads are going to be transferred from the rail car to the track system. And if you want to know a bit more about that, we're going to have a class coming up starting in a few weeks that discusses that and modeling that particular question in greater detail. So this is just, please nobody run out and design anything based on this chart. This is just some things that were in my mind. So you can see that as we have things like a 286 versus a 315K car, we know the nominal wheel load is going to be higher. We don't know exactly how much higher the peak vertical load is going to be, but this is our key output and is a major element in the process that we're going through to develop a holistic model to take input wheel loads, suspected wheel loads, and actually be able to chase that load all the way through the tie and fastening system through all these components you see up here. Once we know that input load, so we got the load up here at in the X and Z direction. Once we can quantify this load up here, we need to figure out how it's transferred through the system, as I referenced earlier. And some of the students in our team that were awake in their statics classes and their physics classes back in the day and know how to draw free body diagrams came up with this little sketch while they were at Murphy's or something, and it shows all of the possible load transfer paths through the system. It doesn't show friction, so there's some other forces in here that we've neglected, just like your intro physics classes typically do. But in short, it's a very complicated system. There's a lot of different interfaces. There's a lot of different coefficients of friction throughout this. So just have this picture in your mind as we talk about the field testing here in a little bit later. So now this is great. What we've said is we've been able to quantify the load, or we're on the verge of quantifying the load at the wheel rail interface, coming up with distributions for those loads, and now we're chasing it through, at least qualitatively, chasing the load path through the fastening system. So now once we get to the load gets to the rail seat, what would really be nice is to have a way of relating wheel rail loads to rail seat loads. You can imagine if you've been through any structural design class that having the rail seat load for a concrete tie is a key input parameter if you're going to design the tie. You don't really care what the wheel rail load is because part of it may be attenuated through all of these products that are sitting on the front table up here. So there currently are quite a few different methodologies, and this was developed by Chris Rapp, some really cool work to compare some of the existing methodologies for calculating rail seat loads, and you can see that there's a significant spread, and the good news is we're going to further complicate this by probably developing our own curve through our work that allows us to determine what the rail seat load is. But this is really the name of the game. If you come in with a rail seat load, if you come in with a wheel load, and you know with a high degree of certainty what the rail seat load you should expect is, you're in good shape in terms of designing the cross tie. You okay on this so far? You can ask me any questions. Nobody's fallen asleep yet. That's kind of exciting. It's not the case for all seminars. Yeah, Laura.
This has to do with the graph that you said not designing anything on this, but how do you take trains that have combined cars, like it has some 15 cars and some?
That's a really great question, and we actually have amazing results to show that, because we made up the question for those of you all out there in cyberspace is that how do we account for trains that have various types of cars, that have all different types of axle loading? And we actually ran all of our experimental work in the field is based on a train that's made up of just that, all different types of axle loads, because we wanted to vary the axle loads. So can you hold on to that question? Maybe you'll like my data later. All right, so now what I want to talk about are some of the key research thrust areas here within RailTEC. First, materials research. And this is some work that Ryan Kearns did, and what we concluded through this research, where we were effectively applying a normal load to a mock concrete tie rail, a mock concrete rail seat, and then applying a lateral force to see if we could generate abrasion. What we found is that we could certainly generate abrasion, but it wasn't incredibly repeatable, and it was hard to link back to some of the input parameters. So we then kind of changed the focus of that test. We checked off the box that abrasion is a feasible mechanism for rail seat deterioration, which is a big discussion point in the rail industry. And we looked into a different topic, which is monitoring the frictional coefficient of various materials under different normal loads. But why is this important? Well, if you think back to that earlier slide in the presentation, where we have all these parts that are smushed together in a system and are attached effectively via some type of clamping force by the tension clamp or the rail clip, and then we have parts in there that are of different materials and different geometries that are held together at times by friction. And then you think about the fact that we're applying lateral forces as the wheels go down the track. That's what you should be thinking about in terms of the applicability of this particular research. So what Ryan has shown is that how the frictional coefficient, number one, deteriorates over time, over loading cycles. And this 400 loading cycles experiment is meant to simulate a unit coal train, and it also, they deteriorate, or we have a decrease in frictional coefficient as we increase the normal force. So that's one thing to think about. And also, there are many different materials that are used in the industry to form these rail pads. So here's a comparison between polyurethane and nylon 6/6, two common materials as they're being rubbed against the concrete, and how their frictional coefficients vary. So just keep in mind that if you understand how these materials perform in terms of their frictional behavior, there may be a way that we can engineer a system with improved frictional properties that either minimize or increase the slip and the slop within the system, if you want to think of it that way, depending on what we really need.
The x-axis is really unit loading cycles. I mean, it's not 400,000.
No, it's 400.
So
it was a very aggressive test too, we should say.
Lost half of its coefficient of friction.
Yeah, over the course of
cycles.
It's an aggressive test, but those loads shown in the previous slide are representative of what's seen in the quote-unquote real world. So the next work that we did was work that looks like this, which is a test that is being carried on right now by Emily Van Dam, and it allows us to take mock concrete specimens that look like this, drop them in these rings, these circles that turn and effectively abrade the material away, and we can compare the relative abrasion resistance between these different specimens. So this machine is downstairs in the crane bay if you'd like for Emily to give you a free tour of it. So some of the work that we've done on that is looking at how different mineral admixtures affect our abrasion resistance. And you can see that certain amounts, like 15% of fly ash, addition of fly ash, actually increases our abrasion resistance. In other words, it decreases our wear depth that we're measuring after these tests that run for about 100 minutes. There's long reasons that both Emily and Professor Lang can give you for why we think that 15% fly ash is performing well as compared to 30% fly ash. Additionally, we did things, and I apologize for the acronyms on here, but a few things I'll point out. This is metallic fine aggregates is the lowest curve here. Once again, we have test duration on the x-axis and we have wear depth on the y-axis. So metallic fine aggregates relative to our control sample, same control shown on the previous screen, these perform very well. So this is actually adding metallic materials into the concrete mixture. And we actually have ties out in the rail industry that are called anvil top ties that are designed very similarly to how this mixed design is put together. So just a couple of tidbits there. We have all kinds of presentations that go into greater depth on this. Lab instrumentation, some cool stuff here. So as I enter into the lab experimentation portion of this presentation, I want to briefly introduce a couple of the final deliverables and objectives of this major FRA tie and fastener BAA. And one of the key deliverables is developing recommended practices that are based on mechanistic design. Another is to increase safety and life cycle of these components, increase the safety of our infrastructure and increase the life cycle of these components. And we think that we can do that through lab testing, field testing, and modeling that I'm going to describe here in a couple of minutes. So here's the three key areas: modeling, the lab study, and the field study. There's a bunch of inputs. Many of these inputs I just talked about in the intro slides, and there's a series of outputs, deliverables to the FRA and the railway industry that ultimately result in improved recommended practices. All of these areas of the project are interconnected. We're going to first start talking about the lab study, which feeds into our finite element modeling. It also guides us as we develop our instrumentation plan for the field study. So there's a significant amount of coordination on our team, and we have a lot of fun, but also a lot of time in meetings to discuss the coordination between these areas. I'm going to only highlight a couple of areas with respect to the laboratory work, and this is kind of hot off the press, so I'm excited to talk about it, but you can direct all your questions to Brent Williams, because I'm excited about this work and where it's headed, and it's just really come out in the last couple of weeks. But one of the major areas in the railway industry in this specific domain of ties and fasteners that needed additional investigation is how much of the lateral force that's applied to the rail gets transferred into the shoulder. This is important because we see a lot of failures in and around the shoulder and the parts that mate with the shoulder. So what our team has done is has taken one of these shoulders, has actually shaved off a part of the shoulder, and has put a beam that they can use that's instrumented with a strain gauge, so we can actually conduct a 4-point bending experiment. And here it is installed. So we did some tests up at the Advanced Transportation Research and Engineering Laboratory. Brent, can you send it around, or has it already gone around? Oh, here we go. Here's the beam and the shoulder. So this is just one example of data that was collected up there. The blue line on the top is the lateral load that was applied by the actuator, and the red line is the shoulder insert force. We can spend a lot of time talking about this, but what I want you to understand just from this this snapshot of data that we collected up there is that at this particular L over V ratio, so lateral to vertical load ratio, and 32.5 kip vertical load, which this is a representative kind of high-end type load, and a severe L over V ratio, we see that nearly half of the load is being transferred through the shoulder face. This is important because the rest of the load is being transferred through friction or through the clip or through other components. So keep this in mind, and this kind of rough 50% number. This is the first time we think this has ever been measured anywhere, and Brent's going to be spending his spring break in beautiful Colorado to try to see if this is feasible to deploy more broadly. But we're going to be talking about this with the modeling effort a little bit later. So what we were looking at a second ago is effectively this data point right here, the 0.5 or 0.52 L over V. But you can see as the L over V ratio on the x-axis is it's increasing, we have a higher percent of the load transferred into the shoulder. Kind of makes sense, right? You have more of the load being transferred laterally into the shoulder. As that resultant force moves downward, you're not going to have as much. You're going to rely on friction less and on the shoulder more. So this is cool stuff, Brent. It's going to be a major part of our instrumentation program this summer when we revisit TTCI, and we're very excited that we've come up with not just one, but two technologies that we think are viable candidates for measuring this force in the shoulder. And for those of you all on the phone that have tried to tackle this problem for quite a while, we're pretty excited to get to present this to the industry once we have more data from our work here in the lab and in the field. In addition, some of the laboratory testing has been centered around the use of these sensors like the one that I'm holding here in my hand. And what this sensor allows us to do is capture the pressure distribution on the rail seat. This is work that's been led by Chris Rapp as well, and it's allowed us to really understand what the different pad materials mean in terms of the load transfer at the rail seat. So it's pretty cool. You can see 3 different stiffnesses effectively of pad materials here and what the different resulting maximum pressures are. And this is important because we think that we're at the point, we're either at the point or close to the point of exceeding some of the allowable stresses for the concrete in terms of actually crushing the concrete, and that being a potential failure mechanism for concrete cross ties and specifically their rail seats. So this work, it's still, it's allowed us to compare different L over V ratios, and we understand the relative differences both in the lab and the field, but with respect to the viability of the crushing mechanism, we're still not able to, quite at this point, conclude whether crushing is viable. Other laboratory instrumentation has been led by Sihong Wei and Professor Dan Kuchma. There's a lot to talk about, and they can give you full presentations on each aspect of the lab instrumentation. And then finally, for its last thing I'm going to say about our lab work is this particular device here. This is the first time it's been unveiled in public. We're going to be developing a full-scale track response experimental loading system, which is going to be housed here at the University of Illinois, and it's going to allow us to apply a variety of loads to an actual track bed with full support conditions. And this is going to allow us to understand the response of the system under a variety of input loads. We're extremely excited about this. We've had a tremendous feedback and excitement from the industry. The FRA has been supportive and is sponsoring the development of this. And we're actually going to apply our loads using an instrumented wheel set. So this is an instrumented wheel set is effectively a strain gauge wheel set that allows you to understand the stresses and strains, and more importantly, back into the input loads that are going into the wheel set, thus the loads that are going into the wheel rail interface. So we're going to have a very good fix on our input loads, which is going to further allow us to capture the exact loads that are entering each of our components that we have laid out on the top screen, or the front row up here. So this is coming soon to a university near you, which happens to be right here. Field instrumentation. This is the part that I'm going to spend a little bit more time on and not go quite as fast because it hasn't been presented to this group, and we really did undertake a very sizable field study. It was the logistics out in the field was led by Marcus Dersch, who's one of the 2 awesome research engineers that I get to work with, and the faculty oversight was Professor David Lang, and it really was a huge experimental program. It's also linked to the laboratory study and the modeling because we're using these field data to validate our FEM modeling, which is the last step that I'm going to talk about today. So some of the goals of field instrumentation. We wanted to lay the groundwork for mechanistic design, understand what the actual loading conditions are out there in the field, provide some insight for future field testing, and collect data to validate our FE model. The FE model is something we're really excited about, and it's really going to be the end device that we actually come up with the recommended practices and run parametric analyses using. We're going to validate it using this field data, and then we're going to all get behind the model and run with the model's results. So here's some of the areas that we investigated in the field. In the rail, we looked at stresses at the rail seat, strains in the web, displacements of the web and base. In the fastening system and the insulator, we looked at the strain of the fasteners and the stresses on the insulators. And for the sleeper itself, we looked at the moments at the rail seat, the stresses at the rail seat, and vertical displacements. We had multiple types of instrumentation. We had some ties, as you can see here, some rail seats, I should say, that are in yellow, that we had full instrumentation on, and other ties we had partial instrumentation on. For each of the 2 sites, we had 15 ties that made up our test zone, and we instrumented the center ties in each one of those zones to try to avoid any boundary effects. Prior to going to TTCI, Professor Kuchma, Marcus, Sihong Wei, and Justin Grasset went to beautiful Tucson, Arizona. We partnered with CXT Concrete Ties, our industry partner. They shut down their facility on a holiday and actually came in and cast ties for us. This is actually vertically oriented strain gauges in the rail seat to show us the strains in the rail seat and give us a feel for what the vertical load is that's being imparted on the rail seat. Once these were removed from the forms, they placed these external strain gauges on the ties and then did some calibration of the ties before they were sent both to Colorado and back here to the lab, Colorado being Transportation Technology Center. So what some of the gauges look like installed, and Sihong's got some ties downstairs right now with the gauges on them if you'd like to take a look. So here's where we were at TTCI doing the field testing. 2 locations. One of them was on the high tonnage loop, or the HTL. It was in a 5-degree curve, and that allowed us to run trains up to about 45 miles an hour. The other location was in tangent track on the railroad test track, which is about a 13-mile loop that allowed us to run a diesel-electric locomotive and a passenger train up to about 102 miles an hour was our max speed. The folks at TTCI were tremendously helpful as we conducted this testing program. So one of the things I thought, instead of listening to me talk about the objectives of the field test program, I'm going to get some water and I'm going to let Professor Lang tell you some of the objectives of the field test program.
Professor Lang, why don't you tell us why we're out here and what we're doing today?
No, I'm not. No audio. All right. We'll give it one try, and if it doesn't work. We conducted some interviews while we were in the field, so we knew when we would come back we would want some at least B-list type movie producer would want to develop a film based on our summer activities. So that's why we were grabbing some videos out there.
Yeah, it worked earlier, so I'm not sure why it's not. Sorry.
So let's pretend that Professor Lane very articulately explains the objectives of the field experiment. Effectively, we had about 10 students out there. We were conducting research to understand how these loads are passed through the fastening system. The loading environment, we had a couple of different things that we were using out there as tools in the field. One of them was the track loading vehicle, which is this amazing machine that allows you to deploy an axle, as you can see here in this image, and apply both static and dynamic type loading conditions. We can determine the track modulus, and it was an extremely helpful tool, as allowing us to validate the model. In addition, we had a freight consist and a passenger consist with the cars that are described there. We had a variety of cars to answer Laura's question earlier, so we could get a variety of axle and wheel loads. So one of the things you have to do is install a lot of clips. So we had a group of professors out there. So I thought for the students in here, you might want to see what it looks like when you're professors, which are experts in their field. What it looks like. You're not going to get any of the field here, the audio, but you're going to see what it looks like to install one of these clips. This is one of the clips like this on the front row here, and you're applying tension to the base of the rail. You can see Professor Lang's excitement about the video as well. That's not too hard, is it? That's Professor Dan Kuchma that installed it, and Professor Lang is supervising there. So for those of you all that have them in class.
Professor Kuchma is hobbling around with some kind of leg injury. I hope there's no connection.
There's no connection, I can assure you that. So here's some of the rail seats. So a couple of images up close. For those of you all that haven't been around field instrumentation, I learned a lot through Professor Lang and through Justin. Justin was kind enough to let me help out a little bit out there, but most of the things I did, I messed up and he had to redo. So here's some of the rail seats that we instrumented, both fully and partially, as we showed on that screen a couple of minutes ago. Let's look a little bit closer at the instrumented low rail, and then we'll zoom in even further on the center rail seat. So what you can see here is that we have instrumentation that allows us to get the vertical sleeper displacement. So I'm going to send this around. If you've never seen what a potentiometer looks like, this particular device, it's in a different frame. You'll see this frame in a minute, but it allows you to measure displacement. Can you send that back? So we use potentiometers to get the global displacement of the sleeper so we understand the track deflections. We also use a potentiometer to get the base displacement of the rail so we know how much it's moving. We have a plethora of strain gauges, more than we care to admit right now, but it took a crew many, many weeks to install the strain gauges that are on the rail that allow us to get the vertical and lateral forces. We also have strain gauges on clips so we understand what the stresses are in the clips as a wheel load passes over. On the gauge side, we have that particular device that's going around as is our fixture to measure the lateral rail displacement. So you got a feel for some of the things that we're measuring. All these different devices feed into this data acquisition system that Justin managed and did an amazing job. There's a lot of wires there. I never understood, you know, everybody talks about getting your wires crossed. I never understood that phrase, what it was about, until I went out there this past summer with this team. So you get all that stuff in the track, it's sitting over here, and then we run passenger trains and freight trains. So if you've never seen a train, here's what it looks like. Here's a passenger train passing our site. We ran up to 102 miles an hour. I believe this is the 90-mile-an-hour pass here. This is our mobile research lab as well. Professor Lang and his team have outfitted this particular Airstream trailer for use in situations such as this. So all of our instrumentation, all of our computers are inside of this trailer, so people are protected from dust and rodents and rattlesnakes in the case of TTCI. And then also we ran freight trains. So if you want to see what it looks like from the instrumentation's point of view, you want to see this, or should I skip this one?
No.
Oh, okay. From the instrumentation's point of view, here's what it looks like with a freight train pass. I think Brandon's in the locomotive too. So you can see the different displacement gauges here on the sides, and we've got all kinds of wires that are sheathed in these PVC pipes here. It's a pretty aggressive environment. You want to have everything taped down and secured. So that freight train that just passed over, what type of loads does it impart on the system? Laterally, you can see that we saw, here's what we've got the max min and the quartiles on here on these graphs that Justin has developed. You can see that we're looking in the 2 to 4 kip range for our lateral loads, which is about what should be expected on tangent track. There's not a lot of high lateral forces on tangent track. So this represents a significant amount of data and replicates because we ran it at least 2, if not 3 times at every particular train speed. So we see there's not a lot, the speed dependency, I'm sorry I didn't point out, this is speed on the x-axis down here and load on the y-axis. So you can see there's not a significant correlation between speed and lateral loads on tangent track. So now you've seen that high-speed test location, so now let's go over to the heavy axle location, and we ran a freight train. So if you haven't seen a freight train, this is what our particular freight train looked like. And the first car behind the locomotive is actually the instrumentation car that is tied into an instrumented wheel set like I described earlier. So the first axle on that first freight car is our instrumented wheel set. Each one of these cars is loaded with beautiful, amazing, valuable Colorado dirt to its gross rail load of anywhere from in the 240s to 100,000 pounds. So 315K cars was the heaviest that we had out there. So now you can see what the lateral loads look like. They're acting on the curved section of track. There's a greater speed dependency here. So we have these curving forces, and by the way, this is on the high rail seat on this curve too. So the balancing speed, despite what that slide said earlier, is somewhere in the 20-mile-an-hour range. But you can see that they're much higher lateral forces here, about 5 times higher on average in the curve versus the tangent. So it dictates how you design these components that are having to withstand these lateral forces. Another thing that we were checking this summer is we wanted to understand the deflection, the global deflection of the track, because we feel like the relative difference in the support of each tie has a major impact on how much load is actually being transferred through that tie down into the subgrade. So what we did is we put these potentiometers mounted on rods that were driven down into the ground really far by people that are much larger than me. Drove these rods down into the ground really deep, and here's what happens when a train passes. You can see that potentiometer is gonna, you can see it moving up and down as the stroke is varying on it. It's touching the top of the tie. So we're getting the tie movement, the total track movement relative to the center of the earth, if you will. And this is important to us because there was a significant variability in the deflection that we've seen under each of these ties, as evidenced by this graph here. So what we have is the vertical load being applied, and this was a static vertical load. It was being applied by that track loading vehicle, and the displacements on the y-axis there. So you can see for the low and for the high rail, there was significant differences, and despite our efforts to tamp the track evenly and have a uniform track section, we didn't have enough tonnage that ran over the site prior to conducting these tests, so we had a lot of variability, and that's something we're planning to change this particular test, although it does give you another manipulation of an experimental condition. Here's our static deflection. So this is for one of those rail seats that I've shown, what the static deflection we found did is actually defines the frontier of these displacements. And when we collect our actual field data, these are our wheel passes on the passenger, on the freight train. What this actually shows us is where the actual displacements are. And we see that there's something like for 60% on the passenger and 75% on the freight. So we don't ever reach this maximum static deflection that we saw using the TLV. And this makes sense because we have these moving loads and the track structure doesn't have as long to react under these moving loads. Also, another question that we had is really how does the speed relate, how does sleeper deflection relate to train speed? So you can see here that we have, and these represent, each one of these X's actually represents 88 data points. We need to put some error bars on here in the future, but represents about 88 data points in terms of axles and replicates. So what you can see here is that the deflection of the whole track structure is not incredibly dependent on speed. As a matter of fact, you see pretty much nothing in the passenger and a very slight increase in the freight train. So, yes, sir, Ernie.
It might be well to point out that the soil that's out there
Mm.
is a fairly granular soil and not a clay, so that the difference in static versus moving loads would be greater under different conditions.
Professor Berenberg points out a couple of good things that I forgot to mention. Number one, this is it's a granular soil out there, and it's not like a clay or some of the other poorer soils that are more indicative of the rest of our rail network, so it's a very stiff subgrade out there. So that's something that we have to understand as we're interpreting any of these results and as we're calibrating the finite element model. TTCI is as a matter of fact, they have to import in poor soil just to conduct tests out there. They bring in clays from Mississippi just so they can conduct
That came from the Waterways Experiment Station.
down in Mississippi.
Ernie Seelig and I did that.
Thank you, Professor
Riley,
Thompson.
your record shows
Yeah.
only about 2 millimeters of deflection.
Yeah.
That in your film with the pot, it looked a lot more.
Yeah, I don't think we grabbed that in particular.
Okay.
This is looking at, now we've zoomed into one particular rail seat here because it gets complicated on this slide if you look at multiple rail seats. We had 6 different places. We were measuring displacements at 6 locations at each of those two field installations. So that's some of what was done in the field. How about some analytical methods here? So let's finish out by talking about the finite element model and some of the things that we're hoping to accomplish through the finite element model. Once again, it's a critical element of the project. It connects to both the lab study and the field study and has really given us significant insight into where we might place instruments, what type of information we need to be collecting in the field and the lab. And it's been an amazing experience so far. This work has been led by Professor Bassam Andraus in our structures group. Postdoctoral researcher Muchel Shen and George Chen are the two folks that are working on it full time for Professor Andraus. So here's what we're doing. We're trying to take this complex system and represent it in finite elements. And you can see that we've done it component by component. This is an example of a rail clip and the rail clip model. So individual components over the past year and a half have been modeled, and they've each been validated through some methodology. The rail clip is relatively simple. We have manufacturer's data, effectively force displacement type data for these components, and then we validate our model based on the manufacturer's data to see if they agree. And for the clip, we had really strong agreement. You're effectively applying an upward force to the toe of these clips to see how much it displaces for a given force. We also spent a lot of time interfacing with Professor Tutumler and his group to accurately model the support conditions for the tie. We're focused only on the tie, so we don't want to get too caught up in the substructure, namely because Professor Tutumler is doing an amazing job within his group of modeling ballast through different methodologies, such as discrete element modeling. So we've got a model of the tie and then the support conditions. One of the biggest challenges is that outside of Ryan's work that I started talking about earlier, when we actually came up with these numbers for the coefficient of friction, we don't have a feel for what the coefficient of friction would be at these other interfaces. So right now we're taking stabs at what the coefficients of friction would be, and this is something that we hope to monitor in the lab through work that Chiagu and Brent are doing, and be able to feed that back into our finite element model to develop more representative models. But we're getting somewhere, and I'm going to show in a minute some of our preliminary results from this. For the tie level, or the single tie models, we've been using the SLTM machine that I showed earlier to validate that that work, and there's a good partnership between the lab team and the modeling team for those validations. Also in the field, what we're doing is we're using that TLV data that we talked about earlier to develop a multiple tie model to be able to look at the forces as you apply a single wheel load, how is it distributed over multiple ties. One thing that I didn't talk about with the field data, and I think that at some point we should get a more focused seminar just on the field data, is that we undertook some efforts to be able to calculate the rail seat loads. And one of the things that we found is that there's a huge variety, mainly determined by support conditions and what loads are actually being accepted by the rail seat. So you put an input load into the wheel rail interface, and you may get from 20 to 90% of that load being accepted by the rail seat immediately under it, depending on the support conditions. So we're working to further iron that out, and this model is going to be a key tool to help us do that. So the only output I'm going to show you from the model right now is an exciting slide that goes back to, if you look over here and you think back to that free body diagram, several of the interfaces in the free body diagram are represented in this particular sketch. And I want to draw your attention to this blue line. The top line here is the lateral load that's applied to the system under a constant 36 kip vertical load. So we're holding the vertical load and applying a lateral load. Same thing roughly the same thing that Brent did in his experiment up at Atrel that I was showing results from earlier. And you can see that this insulator post, which effectively is the forces that are being transferred into the shoulder, is about 50% at these higher L/V ratios. So this is kind of our first step at validating the effects of friction in the system using actual experimental data in the lab and comparing that to our model output. So we're pretty excited, and we're going to move forward with further refining this model and capturing more data here in the lab and in the field. We're going to look at additional comparisons. We're going to do large-scale modeling, apply more realistic loading. Ultimately, we've got to be able to do dynamic loading in our model, which is a challenge, and then conduct a number of parametric studies. I was alarmed yesterday or the day before in a meeting where one of the students calmly spoke up and said that we have, in terms of second-order effects, we have 3.5 million second-order effects to investigate in terms of this tie and fastening system. So sounds like a couple of PhDs right there. So finally, future work. Here's what we're working on. This is kind of the near term, and let's say within the next year. More data analysis. We really are fascinated by the lateral load transfer, and the entire instrumentation plan that Professor Lang is leading along with Ryan Kearns is going to focus on the field work. It's really centered around measuring lateral loads out in the field. So we really want to be able to capture exactly what the lateral loads are. Oh, this is running long, sorry. Just about finished. So we're going to focus on lateral loads in the field and analyze that data, validate the model, we already talked about that. And really this instrumentation trip focusing on lateral loads is something that's never been conducted in the industry thus far. We really don't have a feel for what the lateral loads are that are being seen, thus we don't have a lot of design requirements based on lateral loads. So it's really hard right now to design fastening systems without the understanding of what lateral loads are being imparted on the system. So that's going to be the main thrust of our instrumentation trip in late May of this year when we go back to TTCI. And then ultimately we're going to take small parts of our instrumentation plan and deploy them on the Class 1s. So here's some of my thoughts on where we're going in the future with these components. I'm sold on concrete cross ties and fastening systems. I know that they have a role within North America, and more importantly, I think they have a larger and larger role, especially as we have shared corridors and these shared infrastructure locations where we need to run passenger trains on heavy axle freight infrastructure. So I think if we pursue mechanistic design and materials choices in terms of concrete materials, other improved plastics, I think there's a lot of low-hanging fruit in terms of research on plastics or other advanced materials. Professor Phil Geil is in the room and has some amazing ideas in terms of other innovative materials. There's other products out there such as tie armor. That's a product that Amstead RPS has developed. I think these are keys. These are Kevlar type materials that are more resistant to some of the loads that are being imparted on the system. I think we need to consider all system interfaces and how they affect the overall system design. So understanding how these components interact. So getting a few of these things on the front table up here, rubbing them together and trying to really understand how they interact. I think that's a key to success. And to borrow from some of the AAR's language, lowering the stress state of the tie and fastening system. This is another approach where we can have larger rail seats. We can have under sleeper pads beneath the pie. I'm getting hungry for lunch. Beneath the tie. These have been exhaustively used they've been used a lot, maybe not exhaustively used. They've been used a lot in Austria with significant success. Also, we need improved design validation tests. Those of us that are on committee 30 know that. And then focusing on system level design. Once we have a grasp of what our components are supposed to do, look at the entire system. Here's the amazing team that I'm very blessed to get to work with on a daily basis. Amazing sunset in the background, reflection. This is Professor Barkin's picture, which I appreciate. Here's some of the research sponsors that have been so kind to fund the support of the faculty, students, and everybody else here that's engaged in this work, and the amazing industry partners that have teamed up with us to work on the FRA tie and fastener BAA. There are a lot of other organizations that have played a major role in serving our research team, and these organizations are made up of a lot of individuals. And many of you out there in cyberspace probably see your name up here, and we are very grateful to you for everything you've done to support us. That's it. Anything else? Nothing.
Do you plan on running anything on the soft grade section out there?
We don't. None of our instrumentation is over that section. The only thing that we can do is we have data from the instrumented wheel set, so we understand the relative difference in forces and stiffnesses between our section and that section. That's one comparison that we can make, but the instrumentation is rather costly. At this point, I don't think we see ourselves putting in another instrumentation. The question was about some of the soft soil conditions at TTCI and whether we could collect data over those portions. Fernando?
Very good presentation. I have two different questions. The first one is, because I don't know much about rail, but one different types of rail decrease or how the law has was done and which rail you are using right now on your modeling or your lab is always is a very common type of rail.
You're talking about 132 versus 136 pound rail? I believe everything is 132 that we're using, and Marcus or Ryan, can you verify this? We've also done some sensitivity analysis with our modeling work, and there's negligible difference too.
And the second question is about the longitudinal load.
Yeah, that's
Thanks.
Thanks. The only thing that's common about the presentations that are given by our group around the world is that in every single presentation, somebody raises their hand and asks about the longitudinal load, and we're going to deploy some secretive technologies at TTCI this summer to try to capture some of the longitudinal movement of the rail. It's considered, the BNSF Railway is very passionate about it. I say secretive in a joking manner because mainly there's not a lot of well-established techniques for measuring that. But you are spot on. We need to measure that, and we need to understand how it relates to all these other forces that are being transferred. And I don't mean like long cycle temperature swings within the rail. You mean braking action, tractive forces, and how those things affect it. So there's two different types of longitudinal forces, and we're concerned in the more instantaneous ones that are governed by tractive effort and things like that. Yes?
Can I ask how much of this would translate to panel track?
To slab track? Or
Yeah, slab track.
a lot of the rail seat loading methodologies and the way that we've instrumented the fastening system would be quite applicable, but yeah, I'd say a significant amount of it actually. There's been a lot.
The fasteners are similar, right?
Fasteners are similar. You can look at many of the slab tracks around the world, and they use a tension clamp, the Vossloh tension clamp that went around the room and looks like a Auntie Anne's pretzel. That's a good point. We'd love to, if anybody's out there in cyberspace and would like for us to work on a slab track and deploy some of these technologies, we'd love to. Yes, sir.
So I could ask several questions. Let me start with one, which takes us all the way back to before the beginning, which is the reason this work started here, you'll recall, was concern related to rail seat deterioration. I think John Zeman is on the line. That was his master's thesis. What have you learned so far about what you think are the most important factors that have been causing that?
I think through our field testing and through what we're starting to see with some of the analytical modeling work, just the relative movement of components is what's leading to all. If there was a widely held view by one of the major railways that is steeped in the tradition of using concrete cross ties, that if we held everything tightly enough, we wouldn't see rail seat deterioration. And through everything that we've seen, through our field testing and through our experimental work in the lab, if you don't have motion, you're not going to have wear and deterioration. So I think that it would largely go to the relationship between clamping force of the clip, the friction of the pad, and the tightness and the tolerances of the shoulder width. It's that combination, that system level combination. But we're also not convinced if you would, ideally you might design a system with very high friction or very low friction, or you might force the friction to one interface, or force the slip to one interface or the other, the one that would have the least wear. But as far as rail seat deterioration, I mean, abrasion is definitely, we concluded that abrasion is very viable, and it's a function of two surfaces being displaced from one another. So I think that would be my answer. You had another question?
If you'll allow me, sure. So the other, of course, overarching goal of your work, as you discussed, is this ultimately this mechanistic design concept as applied to track. And which interfaces concern you the most right now in terms of and again, understanding that we're still in the middle of this project, you don't have all the answers, but what's your insight or your preliminary data telling you about the interfaces where you have, let's say, the highest loads where, and the materials may, or the components may be least capable of withstanding what they're being subjected to?
That's a great question. So the question for the online audience is, what interface are we most concerned with in terms of its susceptibility to failure, and what needs the greatest focus in terms of mechanistic design? It's the rail base to insulator to shoulder. That load path that goes from the base of the rail through the shoulder, the base of the rail through the insulator to the shoulder. On the fastening systems that have those components, that's by a long shot. That's probably the one thing that all the railroads would agree on is their greatest maintenance headache with these ties out there. And it's challenging because it's a relatively inexpensive $1.50 component, but it requires a lot of effort to actually replace it. So finding better materials by partnering with Professor Guile, BASF, these other groups is a high priority, I think. And being able, first of all, to quantify the loads. We were on a conference call this week, and one of the companies that we were talking to was just thrilled that for the first time ever, we may have a quantification of what loads are going through that load path. Because we honestly, nobody knows, so we don't even know if we're in the right ballpark picking materials. We'd expect we're not in the right ballpark by some of the failures that we see in curves. But this is work that, no pressure, Brent, but you're going to figure this out for us. You had a third question?
Well, let me ask one more, and then I'll. Based on the work you've done so far, comparing heavy axle loads and higher speed passenger trains, any sense of what the biggest difference or the biggest potential sort of conflict in terms of the design would be?
And you can't ask me why, but I can tell you that it deals with the rail pad design and its ability to deflect under load, and there needing to be different characteristics to achieve proper rideability and also attenuate loads. There's a lot of conflicting objectives that are trying to be met with the design of the pad, and I think that would be the interface that's the most challenging. And in conjunction, you can't really talk about that without talking about the clamping force that's applied by the clamp, by the tension clamp too. So that would be my thoughts on that. We're hoping to get to conduct some research on that. By the way, thanks. I don't know if there are any questions out there. Thanks for staying too. I'm glad you can thank me later for keeping you out of trouble on Green Street, but I appreciate people staying. I think I was long-winded, but we got a little bit of a late start, so I'll take about half the blame. We'll blame the rest on the computer.
All right, well, thank you very much.
Thanks.